Sorry.
No, for sure.
Hello, good morning. I'm Jay Samuel Combinido from the Advanced Science and Technology Institute from Advanced Science and Technology Institute, and I'd like to present on about quality control on observation from ASTI developed weather stations. And I'd like to talk to you about the history about the deployment of the weather stations in the Philippines. Way back in 2009, the Philippines was um, visited by Typhoon Katsana or Ondoy, and it brought a lot of rainfall, almost I think 600 millimeters in one day, and it prompted the government. The government realized that we don't have enough monitoring stations in the Philippines, so they told us to okay, you deploy several stations in the Philippines so that we can monitor the weather at every 10, 15 minutes or much higher resolution than that. And now that we have deployed around 1,800 sensors, now we are at another different problem, and that problem is to ensure that the quality of data that we share to the public, to the local government units, to the researchers, to the forecasters are correct. So this is a few of the weather stations that we deployed in the Philippines. So we have automated weather stations, automated rain gauges, water level monitoring sensors, in river systems, um, water level sensors with rain gauges, and of course we also have agrometeorological stations for agriculture um, purposes, applications, and much more. We have much more. And this is an example of the deployment that we did. So this is automatic rain gauges. Okay, here's the battery and the data logger, and this is water level monitoring station deployed in one of the rivers. And yeah, I think this is the data logger that ASTI developed for all of this. So, well, this is supposed to be an animation, but what I want to say here is that over the years, since 2011, I think 2010, when we started deploying the weather stations, it has grown to almost 1,800 stations around 2016, and it has reached around 400 million records. And these 400 million records has been useful for researchers in the Philippines and forecasters at the local government unit. So over the years, we have realized that the demand for this data in the Philippines has increased as well, and it has a lot of different uses. For example, in forecasting um, field, they use the ground weather data for flood forecasting, rainfall nowcasting, and even just the simple weather monitoring. And on the local government unit side and the national disaster risk reduction management side, they're doing it for decision making, when to evacuate, when to tell people to be alert to and other things like that. And on the academic side, okay, they use this ground weather data to uh, perform weather research, and that weather research could be weather modeling, it could be data assimilation, could be validation of satellite images, satellite rainfall estimates, and we have seen that the demand of this has grown quite large. So one of the things that has bothered us that these stations are machines. These stations are equipment, and they are designed to fail eventually. And it is not far fetched. It is not far fetched that these stations will read will record some unusual data. And for example, this is one example of a report given by us by a user, Project NOAA, and they saw that there is around 50 50 millimeters of rain in 15 minutes. That doesn't happen in the Philippines. So the question is, do we want to share that kind of data? Do we want to share that data without even doing quality control on it? And if you do research on it, if you use it for your research, for your forecasting, it will, the results, the effects will be catastrophic. So that's why we did quality control on the weather observations. So the challenges here is that if you deploy several stations, 1,800 or more, it will be, logically difficult for us, ASTI, to maintain and monitor all stations. So we cannot assign one person per station. So it's very costly. And for for the end user side, okay, the correctness of the measurements matter. Okay, and uh, and the correctness is very important to them. So the motivations of data quality control is that one of the main reasons why we do this is that is to make it easier for data users to identify suspicious and erroneous data and to highlight corrected values. Okay, one of it, and another one is to avoid the issuance of warnings or advisories based on anomalous data, minimize analysis and weather prediction errors, identify calibration, measurement, and communication errors, and possibly detect the deterioration and malfunction of the sensors. Okay. So this is what we did. So each measurement or each station of the data undergoes several steps of quality control. First one is the geolocation check, which just checks if the location, the geo information of the station, latitude, longitude, elevation are correct. Okay, and later on it will be used for the spatial consistency check. The second check is the timestamp check. Okay, if you deploy sensor, you expect that it will give data at this time, it will give data another time. So if that data deviates, if the timestamp deviates large from the expected timestamp, we will flag it. The third one is the range check. So you just want to check if the data fits the range of thresholds, okay, of the data. And the step check, okay, is more of a temporal check. It just says that limits the difference between values between successive, measurements. And then the persistence check ensures that the values are not stuck as a single value. And the internal consistency check ensures that the data it measures, for example, temperature, is consistent with the dew point temperature. The rainfall should be consistent with the the humidity measurement. And for example, the wind speed should be consistent with the wind direction measurement, and so on and so forth. And finally, the spatial consistency check or the body check. So what it does is it checks if the measurement is consistent with the measurements of stations around its surrounding stations. So yeah, the geolocation check will be used for spatial consistency check. And this map here is actually the adjacency network of your AWS station. And actually, when I did the the adjacency network of these stations, I realized that we still don't have enough stations deployed in the Philippines. I think we have to deploy more. Yeah, still not enough. So this one is just the statistics of the failure rate of the measurements that we of the stations. For example, for air pressure, we have 96 million observations of air pressure, and 8.15% of those failed the timestamp check. 2.73% failed the value check. 1.56 failed the step check. 0.12% failed the persistence check, and then 0.01 failed the spatial consistency, so on and so forth. So of course, you can see here that the wind speed at 2 meters, the failure rate is 65.61%. So that's too high. So maybe we're going to try to tune the parameters of the quality control first. Okay. So after quality control, we also did validation whether the quality control checks were actually effective on reducing the error, at least consistent with the other observations. So what we did was use 14 selected stations where we used the ground truth obtained from Pagasa synoptic station measurements from period 2012 to 2015, and we did the validation for rainfall and temperature. So these are the sites, the green ones are the sites of the Pagasa synoptic stations. And we eventually got this result. Okay, this is the error, and this is the index, which is just the sample that we use. And we can see here that if the bar is closer to 0, means that the error is lower. So when we realized that if we do a quality control check on rainfall observations, you can see that except for these samples, okay, almost all has reduced error. So which is quite good because we realized, okay, that we have much more confidence on the rainfall data that we shared to the researchers and the public. And for the whole statistics, we are actually able to obtain a 0.76% decline in RMSE for temperature and 2.32 millimeters per day RMSE for rainfall. So which is quite good. And what we are trying to do here is that the quality control algorithm is going to be published as well to the public. Okay, the WMO said that all quality control algorithms should be shared to the users, or at least documented fact, because there's no one-size-fits-all way of quality controlling data observations. And this one is to share what we did, and so that the users are able to use or understand the quality control that the flags that we are doing. And I'd like to share to you about the data catalog, the computing and archiving research environment data catalog that we developed, where we share this data to the public as well. So yeah. And future work, okay. So right now we already laid the groundwork for quality control, but needs parameter tuning, and we still need continuous improvement to the algorithm, both in the speed and the algorithm itself. So we also need to do algorithm optimization for this to make the quality control even much more faster. And right now we are embarking on a new project to deploy more sensors, okay, with lightning detectors, and use the lightning measurements to effectively predict thunderstorms and rain, typhoon-induced rainfall in the Philippines. So this is with the JICA and SATREPS project with principal investigator Takahashi Yukihiro from Japan. So yeah, summary, data quality control is important now for us because we already deployed several of them, and now we want to ensure that the quality is correct, is good. And then correct observation data is crucial to forecasters, researchers, and decision makers. And of course, if you use the data in your models or in whatever application that you do, if you put in garbage, then you get garbage out of it. So I think that's it. Thank you for listening.